October 14, 2024. A SpaceX Falcon Heavy rocket lifts off from Launch Complex 39A at NASA Kennedy Space Center in Florida. The launch window is 15 seconds wide. The weather is nearly perfect. At 12 minutes past noon Eastern Time, the rocket clears the tower and begins to climb. Strapped to the top of it is NASA Europa Clipper, the largest planetary science spacecraft NASA has ever built, costing approximately $5.2 billion to develop and launch. Its destination is a moon of Jupiter that, for most of the 4 centuries since its discovery, was treated as a curiosity. A small, pale, almost featureless body in the shadow of the largest planet in our solar system that has changed. Because beneath Europa's smooth icy surface, almost certainly, there is an ocean larger than all of Earth's oceans combined, an ocean that has likely been liquid for billions of years, an ocean that, according to a growing body of evidence, some of it confirmed, some of it disputed, some of it still being argued over in the most recent literature, may be one of the most promising places in our solar system to look for life beyond Earth. Europa Clipper is on its way. It will not arrive at Jupiter until April of 2030. The journey involves a Mars gravity assist in March of 2025, an Earth gravity assist in December of 2026, and finally, after 1.8 billion miles of travel, an insertion into Jupiter orbit. Once there, it will perform 49 close flybys of Europa over a primary mission lasting until 2034. This video is about Europa, about what we know, what we think we know, what we have been wrong about, and what one of the most expensive planetary science missions in NASA history is actually designed to find out. It is also about something more specific. Because, in the lead-up to Europa Clipper's launch, a particular question dominated the popular conversation about Europa. The question of whether the moon vents water vapor into space, and whether spacecraft could fly through those plumes to sample the ocean directly without ever needing to land. The story of those plumes is more complicated than most coverage has captured. The evidence for them has been built, challenged, defended, challenged again. The most recent science, published just months before this video was made, has shifted the picture in directions that the popular framing rarely tracks. Let me show you what the actual evidence says. The full picture, not just the dramatic version. Europa is the 4th of Jupiter's large Galilean moons, named for the group of moons that Galileo Galilei first observed through his telescope in January of 1610. It is smaller than Earth's moon, about 90% of the size, and orbits Jupiter at a distance of approximately 671,000 kilometers, completing one full orbit every 3.5 Earth days. From a distance, it appears almost featureless, smooth, pale, almost perfectly white. That smoothness is the first unusual thing about it. Most solid bodies in the outer solar system are heavily cratered. Billions of years of impact events leave their marks. Europa, by contrast, has almost no craters at all. Its surface is geologically young, resurfaced repeatedly by some internal process that has been erasing the evidence of impacts almost as fast as they occur. That resurfacing was always interesting, but for a long time it was treated more as an engineering puzzle than as a habitability clue. The first close-up images of Europa came from Voyager 1 and Voyager 2 in 1979. The images they returned showed something unexpected. Europa's surface was covered in long, dark, reddish-brown streaks, linear features that cross each other at various angles, forming a pattern that looks, at certain scales, almost like the cracked shell of a hard-boiled egg. These features were named lineae. Scientists proposed that they were fractures in the ice, cracks created by some internal stress, stained brown by material welling up from below. The hypothesis that Europa might have a subsurface ocean was actually proposed even before Voyager, based on theoretical work that suggested tidal heating from Jupiter could maintain liquid water beneath an ice shell. But the Voyager images, while consistent with that hypothesis, did not confirm it. The cracks could have been produced by other mechanisms. The reddish staining could have come from various sources. The case for an ocean was a reasonable inference, not a verified observation. That was the picture as of 1979. A cracked, icy world. Interesting, probably dynamic in some way. But the nature of that dynamism was still unclear, and the case for liquid water beneath the ice rested more on theoretical models than on direct evidence. Then came Galileo. NASA's Galileo spacecraft arrived at Jupiter in December of 1995 and spent the next 8 years conducting a comprehensive study of the planet and its moons. The mission had been long planned, originally scheduled to launch in 1986, but delayed by the Challenger disaster and other complications until it finally launched in 1989. By the time it arrived at Jupiter, the spacecraft was already a decade old by the standards of its design. During multiple close Europa flybys, 11 of them in total, with the closest, called E12, occurring in December of 1997 at an altitude of approximately 200 kilometers above the surface, Galileo's magnetometer, the instrument designed to measure magnetic fields, detected something that changed the conversation entirely. Europa has an induced magnetic field. This phrase deserves to be slowed down for, because it is important. An induced magnetic field is different from an intrinsic magnetic field like the one Earth produces. An intrinsic field is generated inside a planet by motion in a conductive core. An induced field is a response to an external field. Europa is sitting inside Jupiter's enormous, constantly rotating magnetosphere. Something in Europa's interior is responding to that external field by generating a magnetic response of its own. A response that varies in just the way it would if there were a layer of electrically conductive material inside the Moon, reacting to Jupiter's changing field as Europa orbits. The only material that fits this description, in the right quantity, at the right depth, with the right electrical conductivity, is a layer of salty liquid water, not ice. Liquid water beneath the ice. That single measurement, the induced magnetic field detected by Galileo's magnetometer team, led by Margaret Kivelson, moved the Europa Ocean from speculation to near consensus. It did not confirm life, it did not confirm habitability, but it established that the physical prerequisite for life as we understand it, persistent liquid water, almost certainly exists beneath Europa's ice shell. The induced field measurement is, to this day, the strongest direct evidence we have for Europa's subsurface ocean. It has never been seriously challenged. It is part of the bedrock of modern Europa science, so this is the baseline, a sealed, icy moon, a hidden ocean. The standard picture, as it stood at the end of Galileo's mission in 2003. What happened next is where the story gets more complicated. This video is about Europa, and it is also about Europa Clipper. And it is, more specifically, about what Europa Clipper is going to find when it arrives, what it has been built to look for, what the evidence pointing toward those targets actually says, and where the strongest and weakest pieces of that evidence currently stand. By the end of this video, you will understand the actual scientific status of Europa's plumes, not the simplified version, not the marketing version, but the version where some evidence has been confirmed, some has been challenged, some has been retracted in everything but name, and the entire question is now more genuinely uncertain than the headlines have generally captured. You will understand the difference between what is solid, like the induced magnetic field, and what is contested, like the plume detections. You will understand what Europa Clipper's instruments can actually tell us, and what they cannot. This is not a doom-mongering video. It is also not a pure cheerleading video. The honest version of this story is, as is so often the case, more interesting than either of those framings. So what does the evidence for Europa's plumes actually look like? Why has it been so heavily contested? What did the Hubble Space Telescope actually detect and not detect in 2012, 2014, and 2016? What did the reanalysis of Galileo data in 2018 claim? And what did a more recent reanalysis in 2026 say in response? What did the James Webb Space Telescope find when it pointed its infrared eye at Europa in 2023? And what did it fail to find? And what does Europa Clipper, currently in transit, expect to encounter when it begins its 49 flybys in 2030? These are the questions this video will answer. Stay with me. Quick pause. If you're enjoying this kind of slow, careful storytelling, hit subscribe. Galaxy Pulse goes deep on stories others rush through. Now, back to Europa. The story of Europa's plumes did not begin with a dramatic discovery. It began, as so much of modern space science does, with an indirect detection at the edge of statistical significance, in data that was originally collected for a different purpose. In December of 2012, the Hubble Space Telescope's imaging spectrograph was observing Europa as part of a broader study of Jupiter's icy moons. The goal of the observation was to characterize Europa's exosphere, the extremely thin layer of gases immediately above the surface, by looking for hydrogen and oxygen emission lines in the ultraviolet part of the spectrum. These elements are produced when water ice on the surface is broken apart by Jupiter's radiation environment. The observation was led, in its analysis phase, by Lawrence Roth at the Southwest Research Institute in San Antonio. Roth and his colleagues were not expecting to find plumes. They were trying to map the distribution of hydrogen and oxygen around the moon, to understand the atmosphere in better detail than previous observations had allowed. What they found, in 3 out of 10 observations, was a hydrogen and oxygen emission signal near the south polar region of Europa that was more concentrated, more localized, than a simple exospheric model would predict. The signal was faint. Its statistical significance was marginal, close to the noise floor of the instrument, but it appeared to be pointing toward a specific region of the surface, rather than being distributed uniformly around the moon. The team published the result in 2014 in Science. The interpretation they offered was carefully worded. The observations were consistent with a transient enhancement of water vapor, possibly indicating localized venting from the south polar terrain. The paper acknowledged the uncertainties. It called for follow-up observations. Those follow-up observations are an important part of the story that rarely gets emphasized. Roth and colleagues conducted additional Hubble campaigns in 2014 and 2015, specifically targeting the location where the 2012 detection had appeared. They were looking for repetition, for confirmation, for evidence that what they had seen was a recurring phenomenon rather than a one-time fluctuation. They did not find it. Subsequent observations of Europa, using the same instrument and the same technique, failed to detect any similar emission anomaly. This was a critical and underreported result. In the world of single-detection scientific findings, the failure of follow-up observations to reproduce a signal is not proof that the original signal was wrong. It could be that the phenomenon is intermittent, rare, or otherwise difficult to catch, but it is also not evidence that strengthens the original finding. It is, at minimum, a caution flag. The honest summary of the Roth 2014 result, as it stands today, is this. a marginal significance detection that was never independently confirmed by repeat observation, and that the original team itself was unable to reproduce in subsequent attempts. This does not mean the plumes are not real. It means the evidence for them, from this first line of investigation, is weaker than popular coverage has often suggested. It is worth noting, in fairness to the original detection, that the failure to reproduce a transient phenomenon is not the same as the failure to confirm a steady-state phenomenon. If Europa's plumes occur only rarely, say, once per year or once per decade, then the probability of catching them with any single Hubble observation campaign is low. The follow-up campaigns by Roth's team would not necessarily have been expected to find plumes, even if plumes do occur, simply because the observation windows are short and the events may be uncommon. This is a legitimate point, but it is also a point that cuts both ways. The rarer the events, the harder it becomes to claim that Europa is actively venting water, in any sense that resembles what the popular framing suggests. In 2016, a different team, this one led by William Sparks at the Space Telescope Science Institute in Baltimore, used Hubble in a completely different mode to search for plumes. Instead of UV spectroscopy, they used the telescope's imaging spectrograph to observe Europa as it transited across the face of Jupiter. During a transit, any material extending beyond Europa's limb would, in principle, appear as a protrusion against Jupiter's bright disk, a physical silhouette, rather than a spectral signal. They were looking for shapes, and they reported finding some. In several of the transit observations, a column-like protrusion appeared at Europa's limb, extending up to approximately 200 kilometers above the surface. The reported detections did not appear in every transit, but in 3 separate observations, taken at different times, the protrusion appeared at a similar location, not, as is sometimes reported, at the southern polar terrain, but at a region near Europa's equator, in the vicinity of the P-Will impact crater. When the team cross-referenced the location of this protrusion with the Roth 2014 UV detection, the spatial correspondence was not exact. The 2 detections were in different parts of the Moon, but the existence of 2 independent detection techniques, both pointing to plume activity, even at different locations, was treated by the community as supportive of the broader plume hypothesis. Sparks and his collaborators were scientifically careful. The 2016 paper described the detections as candidate evidence, consistent with plume activity but not definitively confirmed. The paper explicitly documented the team's efforts to rule out instrumental artifacts before publishing. A follow-up paper in 2017 reported another detection at the same equatorial location. This is where the popular framing of the story tends to peak. 2 independent Hubble investigations. 2 different detection techniques, different locations, but both pointing toward active plume venting. The trouble is, what happened after this rarely gets covered. In 2020, a team led by Janot published a careful reanalysis of the Sparks 2016 observations. They examined the data with newer processing methods and additional comparison observations. Their conclusion was that the original Sparks interpretation was, in their words, effectively refuted. The features Sparks had interpreted as plumes could be explained by other instrumental and observational factors that had not been fully accounted for in the original analysis. This refutation did not receive the press coverage that the original Sparks detection had received. It appeared in the technical literature. It was discussed at planetary science conferences, but the popular narrative that Hubble confirmed Europa plumes continued to circulate largely unchanged, even after one of the 2 pillars of that narrative had been substantially weakened. This pattern, original dramatic detection, much later careful refutation, asymmetric press coverage, is one we have seen in other Galaxy Pulse videos. It is not a conspiracy. It is a structural feature of how science journalism works. Confirmations of dramatic claims receive more attention than refinements and refutations. The result, over time, is a public picture of any given scientific question that tends to be more confident than the actual state of the evidence supports. In 2018, a third line of evidence appeared, one that, on its surface, looked like the most decisive of all. A team, led by Zhiying Jia at the University of Michigan, published a paper in Nature Astronomy titled Evidence of a Plume on Europa from Galileo Magnetic and Plasma Wave Signatures. The paper described a reanalysis of data collected by Galileo's magnetometer and plasma wave spectrometer during the E12 flyby in 1997. The closest Galileo ever came to Europa, at approximately 200 kilometers above the surface. For 21 years, the data from E12 had sat in archives. The magnetometer had recorded an anomaly, a localized perturbation in the magnetic field, lasting about 3 minutes, that did not fit the expected magnetospheric pattern. The plasma wave instrument had recorded a brief burst of activity in the same region. At the time of the flyby, no one had a framework for interpreting these readings as a plume signature, because plumes had not yet been proposed as a feature of Europa. By 2018, with the Roth and Sparks Hubble detections having raised the plume hypothesis to active scientific consideration, Jia's team went back and looked at the Galileo data with new questions. Using updated magnetospheric models and three-dimensional simulations of how a plume would interact with Jupiter's magnetic field, they showed that the E12 anomaly could be reproduced if Galileo had flown through a column of ionized water vapor about 200 to 400 kilometers tall. The paper was carefully framed. It did not claim definitive plume detection. It claimed that the data was consistent with a plume encounter, and that a plume encounter was a plausible explanation for the otherwise unexplained anomaly. The press coverage was, as is often the case, less careful. Headlines proclaimed that Galileo had probably flown through a Europa plume in 1997. The result was treated as a major independent confirmation of the plume hypothesis, a different instrument, a different technique, a different era, all pointing to the same conclusion. For several years, the Jia 2018 paper was treated in popular coverage as one of the strongest pieces of evidence for Europa's plumes. It was cited in articles about Europa Clipper as justification for the mission's plume sampling capabilities. It was referenced as proof that the plumes were not a Hubble artifact, that they were real enough to have left a signature in spacecraft data from a previous mission. Then, in February of 2026, just months before this video was made, that interpretation came under direct, published challenge. A paper by William Patterson and Glyn Collinson in Geophysical Research Letters, titled Galileo PLS Plasma Observations During the E12 Europa Flyby, Refuting an Encounter with a Cryovolcanic Plume, reported the results of an analysis of data that had never been fully processed from the E12 flyby. The Galileo plasma instrument, known as PLS, was capable of directly measuring the density of ions near the spacecraft. If Galileo had flown through a water plume, PLS should have recorded a sharp spike in ion density, a signature that the magnetometer alone cannot uniquely diagnose. The calibrated PLS data from E12 had never been published. For 26 years, it had sat in raw form. Patterson and Collinson reactivated the original Galileo PLS analysis code and processed the data for the first time. What they found was inconsistent with a plume encounter. The ion density measurements near closest approach were in agreement with the background ionospheric density expected from Europa's tenuous atmosphere. There was no spike. There was no signature consistent with a plume. The brief burst of activity that the plasma wave instrument had recorded The same burst that GEA 2018 had interpreted as a plume signature was, according to the PLS measurements, more consistent with Galileo flying through Europa's inhomogeneous ionosphere than with a discrete cryovolcanic plume. The paper's conclusion was direct. They discount a plume encounter during E12. This is recent science. It was published in February of 2026. It has not yet been fully integrated into popular coverage of Europa, which still routinely cites the GEA 2018 finding as confirmed evidence of past plume encounters. The Patterson and Collinson refutation does not prove that plumes do not exist at Europa. It only addresses one specific claim, the claim that Galileo flew through one in 1997. But it removes that claim from the list of supporting evidence. Let me state the implication plainly. Of the three major pillars on which the Europa plume hypothesis was built over the past decade, two have now been substantially weakened by subsequent careful analysis. The Sparks 2016 Hubble transit detection was challenged by Genoa in 2020. The GEA 2018 Galileo magnetometer interpretation was challenged by Patterson and Collinson in 2026. The Roth 2014 Hubble UV detection has never been independently reproduced, despite multiple follow-up campaigns. This does not mean Europa has no plumes. It means the evidence for them is significantly weaker than it appeared to be 3 or 4 years ago. The honest current scientific position is that plume activity at Europa remains possible, perhaps even likely on rare occasions, but is no longer confirmed by any single line of evidence. Then came the James Webb Space Telescope, JWST, launched on Christmas Day of 2021 and operational from mid-2022, brought to Europa observations, an instrument far more sensitive than Hubble across a much wider range of infrared wavelengths. Among its early science programs were observations of Europa, conducted to characterize the Moon's surface composition and to look directly for active plume venting. The plume search was an obvious target. If the Hubble plume detections were real, JWST should have been able to confirm them at higher significance. If active venting was occurring, JWST infrared sensitivity should have detected the spectral signature of water vapor in Europa's upper atmosphere. In September of 2023, the results of JWST Europa observations were published in 2 papers in Science. The headline finding of those papers was the detection of carbon dioxide on Europa's surface, concentrated in a region of chaos terrain called Terra Regio. This was a significant result. The spatial distribution of the CO2, concentrated in a specific area of disrupted terrain, rather than uniformly across the surface, was interpreted by both teams as evidence that the carbon had been transported from Europa's interior to the surface, rather than being delivered externally by impacts or magnetospheric chemistry. This finding strengthens the case that Europa's ocean contains carbon, which is, in turn, one of the foundational ingredients of organic chemistry as we understand it. But the same JWST observations also looked for active plume venting, and on that question, the result was different. JWST found no clear evidence of active plumes at the time of observation. The infrared sensitivity that could have, in principle, detected water vapor signatures from active venting did not detect them. The instrument that should have been able to confirm the Hubble detections at higher significance found, instead, what appeared to be a quiet Europa with no detectable plume activity. This null result has been somewhat lost in popular coverage of the JWST Europa papers, which has tended to emphasize the CO2 finding while passing more quickly over the plume non-detection. But it is a critical piece of the current picture. JWST is significantly more sensitive than Hubble in the relevant wavelengths. Its failure to detect active plumes does not prove that plumes never occur at Europa. It does suggest that, at minimum, the plumes are not common, not continuous, and probably not large in the way that, for instance, Enceladus's plumes are. The picture that emerges from the combined evidence of the past decade, Roth's unrepeated UV detection, Sparks's refuted transit detection, GEA's now refuted magnetometer interpretation, and JWST null result, is not the picture of a moon that is reliably venting water into space. It is the picture of a moon where plume activity may occur, possibly rarely, possibly transiently, but where the evidence remains genuinely uncertain, in a way that the public conversation has not fully tracked. So, why is Europa Clipper still being sent? Why is one of the most expensive planetary science missions in NASA history flying toward a moon whose most discussed surface phenomenon may not exist in the form it has been described? The answer is that Europa is far more than its plumes, and the case for Europa Clipper does not depend on plume sampling. The case for Europa Clipper rests on something much older, much more solid, and much less contested than the plume detections. It rests on the induced magnetic field. It rests on the near-certain existence of a global subsurface ocean. It rests on the documented presence of complex chemistry, carbon, salt, hydrogen peroxide, sulfur compounds, distributed across Europa's surface in patterns that suggest active geological processes connecting the surface to the ocean below. The plume question is, in a sense, a side question, a useful question, because if plumes do exist, and if Clipper can fly through one, the mission gains direct access to material from the subsurface without ever needing to land. But the absence of confirmed plumes does not invalidate the mission. The ocean is real. The chemistry is real. The questions Clipper is designed to answer about Europa's habitability do not require active venting. Let me describe what Europa Clipper actually is, and what it is actually designed to do. The spacecraft launched on October 14 of 2024 aboard a SpaceX Falcon Heavy from Kennedy Space Center. It is the largest spacecraft NASA has ever built for a planetary mission. With its solar arrays fully deployed, it spans approximately 30 meters, longer than a basketball court. The development cost was approximately $5.2 billion over more than a decade of design and construction. The trajectory to Jupiter is indirect. The Falcon Heavy could not carry enough fuel to send Clipper on a direct path. Instead, the spacecraft is using gravity assists, a Mars flyby that occurred on March 1 of 2025 at approximately 550 miles above the Martian surface, and an Earth flyby planned for December of 2026. The combined velocity boost from these two flybys will send Clipper on its final leg to Jupiter, with insertion into Jupiter orbit scheduled for April of 2030. Once at Jupiter, Clipper will not orbit Europa directly. Jupiter's radiation environment around Europa is so intense that a spacecraft orbiting the Moon would accumulate damage from charged particle bombardment faster than its instruments could function. Instead, Clipper will orbit Jupiter in a large, elongated path that brings it close to Europa for short-duration flybys before swinging back out to safer distances. 49 flybys are planned over the primary mission, each one targeting a different region of the Moon, each one carefully timed to maximize scientific return while minimizing radiation exposure. The primary mission concludes in 2034. To put the radiation environment in concrete terms, Europa orbits inside Jupiter's magnetosphere, which is the largest magnetic structure in our solar system, except for the heliosphere itself. The charged particles trapped in this magnetosphere are accelerated to extremely high energies by Jupiter's powerful magnetic field. The radiation dose, accumulated by a spacecraft at Europa's orbital distance, is roughly 1,000,000 times what a spacecraft would experience in Earth orbit. Galileo, during its 8 years at Jupiter, accumulated damage from this radiation that progressively degraded its instruments. By the end of the mission, several instruments were producing data of significantly reduced quality compared to early in the mission. Europa Clipper's design takes the lessons from Galileo seriously. The mission's sensitive electronics are housed inside a vault, a thick metal shielding structure that protects them from most of the charged particle bombardment. The flyby orbit architecture means that Clipper spends most of its time outside the highest radiation regions, only diving in for the close flybys themselves and then retreating to safer altitudes. By keeping the time inside the worst radiation environment to a minimum, the mission can sustain its instrument performance across the full 49 flybys. The spacecraft carries 9 science instruments plus a gravity experiment. Each one is designed to address a different aspect of Europa's habitability. The ice-penetrating radar, called REASON, will use radio waves to probe Europa's ice shell from above, mapping its thickness and internal structure. This single instrument may produce the most consequential measurement of the entire mission. The current debate over Europa's ice shell thickness ranges from estimates of just a few kilometers in the thinnest regions to as much as 30 kilometers globally. Different thickness estimates lead to different conclusions about whether ocean material could ever reach the surface, and consequently, whether plumes are physically possible. Reason will, for the first time, give us a direct measurement. The thermal imager, called ETHEMES, will map Europa's surface temperature at high resolution. If localized warm spots exist, regions where heat from the interior is reaching the surface, ETHEMES will find them. These warm spots, if confirmed, would be candidate plume source locations. The mass spectrometer, called MASSPEX, is designed to detect molecules in any vapor that Clipper happens to encounter, at sensitivities of parts per trillion. If Clipper flies through a plume, MASSPEX is designed to identify the chemical composition of the plume material: water, salts, organic molecules, amino acid precursors, anything that the ocean might have contributed to the venting. MASSPEX is also sensitive enough to detect Europa's tenuous exosphere, which may carry trace signatures of the Moon's surface and interior chemistry, even in the absence of active plumes. The exosphere measurement is particularly important if the plumes turn out to be rare or absent. Europa is constantly surrounded by a thin atmosphere of water vapor and other molecules, produced by the slow sublimation of surface ice and the impact of micrometeorites on the surface. This atmosphere is too thin to support any chemistry of its own, but it carries information about whatever has been on the surface or near it over geological timescales. By measuring the exosphere with high sensitivity, MASSPEX can effectively sample Europa's surface chemistry without needing direct surface contact. The molecules in the exosphere reflect whatever has been outgassing, sublimating, or being ejected from the surface over the relevant timescales. If MASSPEX finds organic molecules in Europa's exosphere, even in trace concentrations, that finding will be informative regardless of whether active plumes are present. It will mean that organic chemistry exists somewhere accessible to the surface, which in turn places constraints on what is happening at depth. The surface dust analyzer, called SUDA, will characterize solid particles ejected from Europa's surface or from any plume activity, providing complementary compositional data to MASSPEX vapor analysis. The ultraviolet spectrograph, called UVS, is the direct successor to the Hubble UV observations that first suggested the plumes in the Roth 2014 paper. UVS will conduct UV spectroscopy of Europa at sensitivities far beyond what Hubble could achieve. and will specifically search for hydrogen and oxygen emission signatures consistent with active venting. The mapping spectrometer, called MIS-C, will produce detailed surface composition maps across the entire Moon, identifying the distribution of salts, organic compounds, and other chemistry of habitability interest. The magnetometer, called ECM, will refine the induced magnetic field measurement that first confirmed Europa's ocean. With far higher precision than Galileo's instruments, ECM will help determine the ocean's depth, salinity, and approximate volume. Together, these instruments are designed not to confirm a specific hypothesis, but to characterize Europa's habitability from every available angle. Whether plumes are confirmed or not, the mission will produce the first detailed survey of an outer solar system ocean world. That, in itself, is a transformative scientific result. Before we go further, let us make sure the underlying science here is clear. Because the rest of this story depends on understanding a few things, and they are not difficult things. They have just been obscured in popular coverage by a combination of jargon and dramatic framing. The first thing to understand is what an induced magnetic field actually tells us. Earth has an intrinsic magnetic field, one generated inside our planet by convection in a molten iron core. We make our own magnetism. Europa does not. But Europa's interior responds to Jupiter's magnetic field in a way that requires a layer of electrically conductive material inside the Moon. The strength and timing of the response are consistent with a layer of salty liquid water located beneath the ice shell, with a thickness of probably 100 kilometers or more. This conclusion has been independently checked by multiple analyses of the Galileo magnetometer data, and by subsequent observations from Earth-based telescopes. It is the strongest piece of evidence we have for Europa's ocean. The second concept is tidal heating. Europa's orbit around Jupiter is slightly elliptical, maintained in that shape by gravitational resonance with the neighboring Galilean moons Io and Ganymede. The three moons are locked in what astronomers call a Laplace resonance, with Io completing 4 orbits in the time Ganymede completes 1. This precise relationship has been stable for hundreds of millions of years, and is what gives Europa its slight orbital eccentricity. Without this resonance, Europa's orbit would have circularized long ago, and the tidal heating that maintains its ocean would have shut down. As Europa moves closer to Jupiter during its 3.5-day orbit, Jupiter's gravity pulls on it more strongly, compressing and deforming it slightly. As it moves away, that gravitational grip relaxes. This stretching and squeezing happens continuously, completing one cycle every orbit. The friction generated by this cyclical deformation produces heat inside Europa's interior. Enough heat, according to current models, to keep the subsurface ocean liquid despite Europa's distance from the Sun. This is a critical mechanism. Without tidal heating, Europa's ocean would have frozen solid billions of years ago. With tidal heating, the ocean has likely been stable as a liquid environment throughout the Moon's history. The same tidal energy may also produce hydrothermal activity at the seafloor, where the ocean meets Europa's rocky interior, a potential energy source for any chemistry that might exist down there. The amount of energy generated by tidal heating in Europa's interior is not precisely known, but estimates range from approximately 1 to 10 terawatts globally, depending on the model. For context, Earth's total internal heat flux is about 46 terawatts, most of which comes from radioactive decay rather than tidal heating. Europa's tidal heat output is smaller in absolute terms, but it is distributed across a much smaller body, and crucially, it is concentrated in the regions where it matters most for habitability, the ice shell and the ocean below it. The same mechanism that drives Io's spectacular surface volcanism, scaled down for Europa's different orbital parameters and internal structure. is what keeps Europa's interior chemically interesting. The third concept is the redox gradient that makes Europa interesting as an astrobiology target. Jupiter's radiation environment continuously bombards Europa's surface ice with charged particles, breaking the water molecules apart and generating oxidants, hydrogen peroxide, molecular oxygen, sulfur compounds. These oxidants are reactive. They have been observed on Europa's surface by Galileo's instruments and confirmed by later observations. If these surface oxidants can migrate downward through the ice shell, somehow, and reach the ocean, they create a chemical disequilibrium with whatever reductants might exist in the ocean from hydrothermal activity at the seafloor. That kind of chemical disequilibrium, a redox gradient, is one of the primary energy sources that life on Earth exploits at deep-sea hydrothermal vents, where entire ecosystems exist powered by chemistry rather than sunlight. To put this in concrete terms, the ecosystems around Earth's deep-sea hydrothermal vents, places where the temperature reaches several hundred degrees Celsius, the pressure is extreme, and no sunlight has ever penetrated, support remarkable biological diversity. Tube worms, crabs, fish, and bacterial mats live in environments that, by most surface life standards, should be uninhabitable. They survive by exploiting the chemical disequilibrium between the hot, reduced fluids emerging from the seafloor and the cooler, oxidized seawater they mix into. The energy that drives these ecosystems is not sunlight. It is chemistry. Specifically, it is the chemistry that becomes available when reduced compounds from hydrothermal sources encounter oxidized compounds from elsewhere in the ocean. The question of whether Europa's ocean has a similar architecture is one of the central open questions in current astrobiology. The induced magnetic field measurement tells us the ocean is there. The tidal heating models tell us that hydrothermal activity at the seafloor is at least plausible. The surface oxidants tell us that the chemistry needed for a redox gradient exists somewhere in the system. What we do not yet know is whether the surface oxidants can actually reach the ocean to participate in that chemistry. The question of whether oxidant migration from the surface to the ocean actually occurs is one of the central open questions in Europa science. The plumes, if they exist, are one possible answer. They would represent a pathway from depth to surface, and by implication, a pathway from surface to depth. The chaos terrain regions, where the ice appears to have been disrupted in the past, are another possible pathway. The fundamental question is whether Europa's ice shell is a permanent barrier between surface chemistry and ocean chemistry, or whether some exchange occurs. If exchange occurs, Europa's ocean is potentially habitable in the deep sense, possessing not just liquid water, but also energy sources. If no exchange occurs, the ocean is still interesting, but its habitability case is weaker. So here is where the stakes start to rise. The plume question, regardless of whether plumes turn out to be common, rare, or essentially absent, is fundamentally a question about whether Europa's ice shell is permeable. And that question matters far beyond the immediate issue of whether Clipper can sample subsurface material directly. If the ice shell is permeable, even occasionally, even in specific locations, then Europa's ocean is not isolated from the surface chemistry above it. The oxidants generated by Jupiter's radiation can potentially reach the ocean. Carbon, salt, and other compounds from the ocean can potentially reach the surface, leaving traces that telescopes and missions can detect. The JWST CO2 detection in Terra Regio, with its concentration in disrupted terrain consistent with internal transport, is the strongest evidence we currently have that some such exchange has occurred at least at some point in Europa's history. If the ice shell is not permeable, if it is, instead, a true sealed barrier, then Europa's ocean has been chemically isolated for most of the Moon's history, and its potential for habitability rests on whatever chemistry was present at its formation, plus whatever hydrothermal activity might be occurring at the seafloor. The ocean would still potentially be habitable, but the case would be weaker. This is the question Europa Clipper is fundamentally designed to address, not just plumes, permeability, the connection or lack of connection between Europa's surface and its ocean, and that question is well defined. It is measurable. It does not depend on whether any single plume detection turns out to be correct. The ice shell's structure, the surface chemistry's distribution, the thermal map of the moon, all of these will tell us, collectively, whether the ocean is sealed or connected. The JWST observations of Europa in 2023 deserve a closer look, because they represent the most recent direct evidence we have, and because the popular framing of them has tended to emphasize one finding while underplaying another. The two papers published in Science in September of 2023 were led by two independent teams. One was led by Samantha Trumbo at Cornell University. The other was led by Geronimo Villanueva at NASA Goddard Space Flight Center. The two teams used slightly different analysis approaches on overlapping JWST data and reached largely consistent conclusions. The headline finding was the detection of carbon dioxide on Europa's surface, concentrated in Terra Regio, a large region of chaos terrain in Europa's anti-Jovian hemisphere, roughly 1,800 kilometers across. The CO2 was identified by its characteristic infrared spectral signature, and its spatial distribution was mapped at high resolution. The interpretation that both teams favored, with appropriate scientific caution, was that the CO2 had been transported from Europa's interior to the surface through the chaos terrain. The reasoning was that carbon dioxide delivered externally, by cometary impacts, by Jupiter's magnetospheric chemistry, or by background cosmic processes, would tend to be distributed more uniformly across the surface, or concentrated at impact sites. The strong localization in chaos terrain, where the ice shows evidence of past disruption, was more consistent with internal origin. If correct, this interpretation has significant implications. It means Europa's ocean contains carbon, and it means that some pathway has existed, at least at some point, allowing material from the ocean to reach the surface. This is a real result, and it strengthens the broader case for Europa's habitability. The presence of carbon in a salty subsurface ocean, combined with the existence of pathways between that ocean and the surface, is exactly the chemical architecture that would support the kind of redox gradient discussed earlier. The JWST CO2 finding is, in my view, the most important Europa result of the past 3 years. But the same JWST observations also looked, deliberately and systematically, for active plume venting at the time of the observations. The infrared sensitivity of JWST in the relevant water vapor wavelengths is far greater than what Hubble could achieve, and active plumes of the scale suggested by some of the earlier detections should have been detectable by JWST if they were occurring. The result was negative. No active plumes were detected. This null result does not appear prominently in most popular coverage of the JWST Europa papers. It tends to be mentioned briefly, if at all, while the CO2 detection receives the headlines. But the failure to detect active plumes is itself a scientifically important finding. It tells us that, at minimum, plumes are not common at Europa. If they exist, they are intermittent, they may be rare, they may have only occurred during specific past epochs that happened to coincide with the Hubble observation windows. They are not, as some earlier popular coverage suggested, a continuous feature of Europa's current activity. The combination of JWST CO2 detection in chaos terrain and JWST plume non-detection is, in fact, the central puzzle of current Europa science. The CO2 finding suggests that surface-ocean exchange has occurred. The plume non-detection suggests that whatever mechanism enabled that exchange is not currently active in any way that would produce detectable atmospheric water vapor. The most natural interpretation of these two findings together is that Europa undergoes occasional episodes of geological activity. Episodes where chaos terrain forms, where material is transported between the surface and the ocean, where some kind of venting or melting occurs, but that these episodes are not happening right now in the regions JWST observed. The geological record is preserved on the surface, even when the activity itself is dormant. Europa Clipper, with 49 flybys spread across nearly 4 years of primary mission, has a much better chance of catching an active venting episode than any single JWST observation could. If plumes occur once per decade, or once per year, or once per month, Clipper's repeated close-range observations are far more likely to detect them than any single telescope campaign from Earth. This is part of why Clipper is still important, even with the recent weakening of the plume evidence. Direct, in-situ observation, repeated over years, is a far more powerful tool for catching transient activity than any number of telescope observations. The history of how the Europa plume story has been covered in popular media is, in my view, one of the more instructive case studies of the past decade in space science journalism. The pattern goes like this. A dramatic new detection gets reported with strong language and confident headlines. Hubble confirms Europa plumes. Galileo flew through a Europa plume. The press coverage exceeds the careful language of the original papers, which typically include extensive caveats about uncertainties and the need for follow-up confirmation. Then, over the following years, the original detection is examined more carefully. Sometimes it holds up. Sometimes it is weakened by subsequent analysis. Sometimes it is effectively refuted, as the Sparks 2016 interpretation was by Jeannot in 2020, and as the GEA 2018 interpretation has been by Patterson and Collinson in 2026. These refinements and refutations rarely receive comparable coverage. They are technical, undramatic, and require the reader to follow a story that has already been declared closed by earlier coverage. The result is that the public conversation about Europa's plumes has tended to remain at the level of the most confident early claims, even as the underlying scientific picture has shifted toward greater uncertainty. Let me give you specific examples of what mainstream coverage has consistently missed. The first is the unrepeatability of the Roth 2014 detection. Roth and colleagues conducted follow-up Hubble campaigns in 2014 and 2015, specifically targeting the location of their original detection. They did not find similar emission anomalies. This non-repetition is critical context for evaluating the original detection. It almost never appears in popular coverage. The second is the Jeannot 2020 reanalysis of the Sparks 2016 transit observations. This careful technical paper effectively refuted the original plume interpretation. It received almost no press coverage. The Sparks 2016 detection continues to be cited in popular articles as confirmed evidence of Europa plumes, even after its primary interpretation has been challenged. The third is the Patterson and Collinson 2026 paper, challenging the GEA 2018 Galileo plume interpretation. This is recent science, published just months before this video was made. It has received minimal coverage outside specialist channels. The GEA 2018 result continues to be cited as confirmed evidence of past plume encounters. The fourth is the JWST plume non-detection. This is a significant result that has been largely overshadowed by the CO2 detection. JWST is more sensitive than Hubble at the relevant wavelengths. Its failure to detect active plumes, while consistent with the plumes being intermittent rather than absent, is important context that rarely appears in coverage emphasizing the CO2 finding. The fifth is the consistent overstatement, in popular coverage, of the certainty of any individual plume detection. The technical literature has been careful throughout. Papers have used phrases like candidate evidence, consistent with plume activity, suggestive of. Press coverage has typically translated these into confirmed, detected, imaged. The gap between the technical hedging and the popular confidence has, over time, produced a public understanding of Europa's plumes that is significantly more certain than the actual evidence supports. The honest picture, as of mid-2026, is this: Europa may have plumes. The plumes, if they exist, are probably intermittent rather than continuous. The evidence for any specific plume detection has been weakened by subsequent analysis in at least 2 of the 3 major cases. The Roth 2014 result remains the only one of the original detections that has not been directly challenged, but it has also never been independently reproduced. Europa Clipper is the instrument that will resolve this, not because it is designed specifically to find plumes, though MASSPEX, SUDA, and UVS are all capable of detecting them if they exist, but because it will conduct sustained, close-range observation of the Moon over nearly 4 years. Whatever Europa is actually doing geologically and atmospherically, Clipper will see it more clearly than any previous instrument. Beyond the plume question, there are several other Europa Clipper objectives that deserve mention, because they are the parts of the mission that do not depend on plumes at all. Understanding what these objectives are, and what instruments will address them, gives a clearer picture of what the mission is genuinely designed to accomplish, separate from any single piece of contested evidence that may or may not still hold by the time Clipper arrives. The first is the ice shell thickness measurement. The current debate over how thick Europa's ice shell actually is ranges across an order of magnitude. Different models, using different assumptions about thermal structure and tidal heating, produce thickness estimates from as thin as 3 to 5 kilometers in some regions, to as thick as 25 or 30 kilometers globally. The implications of this range are enormous. A thin shell allows for the possibility of relatively easy connection between the surface and the ocean, including the kind of pathways that might support plume activity. A thick shell makes such connections far more difficult and pushes the most plausible mechanisms for surface-ocean exchange to specific regions of disrupted terrain, rather than to general permeability. Reason: Clipper's ice-penetrating radar will measure the ice shell thickness directly. This will not be a single measurement. Reason will operate during the close approach phase of each of the 49 flybys, building up a coverage map of the shell's structure across many different regions of the Moon. By the end of the primary mission, we will have, for the first time, a real three-dimensional understanding of Europa's ice. That measurement alone may resolve more open questions about Europa than any plume detection would. It will tell us whether the ice is structured the way models have assumed. It will tell us where the shell is thickest and thinnest. It will tell us whether the chaos terrain regions correspond to regions of currently thinner ice, or to regions where the ice was thinner in the past. Reason is, in my view, the single most important instrument on Europa Clipper, not because it is designed to find life, but because it will resolve the structural question that underlies all the other questions about Europa's habitability. The radar has been designed to penetrate the ice to depths of up to 30 kilometers, depending on the ice composition and structure. It will operate at 2 frequencies, optimized for shallow and deep penetration respectively. The data from each flyby will be combined with data from preceding and subsequent flybys to build up a three-dimensional model of the ice shell across the regions of Europa that Clipper observes most closely. By the end of the primary mission, the shell structure will have been mapped at a level of detail that exceeds anything currently available for any planetary body except Earth. The second, non-plume objective is the surface composition mapping. MISI, the mapping spectrometer, will produce detailed maps of the distribution of salts, organic compounds, and other surface chemistry across Europa. The Galileo near-infrared mapping spectrometer, in the 1990s, gave us the first hints of this distribution, including the identification of hydrated salts that point to ocean-derived material on the surface. MISI will extend that work by orders of magnitude in spatial resolution and spectral precision. The questions MISI will address are concrete. Which surface salts are present, in what concentrations, in what regions? How do their distributions relate to the chaos terrain, the lineae, the impact craters? What organic compounds, if any, can be identified? How does the surface chemistry vary between Europa's leading hemisphere, which encounters more dust and meteoritic delivery, and its trailing hemisphere, which is more heavily bombarded by Jupiter's radiation? The answers to these questions will give us the most comprehensive picture of Europa's surface chemistry that has ever been assembled. And from that picture, we can read backward to learn about the ocean below, what is dissolved in it, what minerals it deposits, what processes connect it to the surface. The third, non-plume objective is the gravity field measurement. By tracking Clipper's exact position during each flyby using Earth-based radio measurements, mission scientists will be able to map Europa's gravity field in unprecedented detail. The gravity field encodes information about the distribution of mass inside the Moon, which means it can constrain the depth of the ice shell, the thickness of the ocean, and the size and composition of the rocky interior beneath the ocean. This is the kind of measurement that does not produce dramatic headlines, but that fundamentally shapes our understanding of what Europa is. The gravity data, combined with the radar data from REASON and the magnetic data from ECM, will give us the first detailed interior structure model of an outer solar system ocean world. There is also a fourth category of objectives worth mentioning, which has less to do with answering specific scientific questions and more to do with providing context for future missions. Europa Clipper, while not itself a life detection mission, is the prerequisite for any future life detection mission. Concepts for a Europa lander have been studied at NASA for over a decade. The Lander Science Definition Team published its report in 2017, identifying 3 top-level science objectives: search for evidence of life, assess the habitability of the ocean, and characterize surface and subsurface properties relevant to future exploration. The Europa lander concept is not currently funded. It is not in active development, but it exists as a scientifically mature design, waiting for the kind of justification that only Europa Clipper can provide. If Clipper detects organic chemistry in the exosphere, in surface ice, or in any plume material it might encounter, the case for following up with a lander becomes much stronger. If Clipper confirms that the ice shell has thin regions where direct surface access to material from depth is possible, the lander design can be optimized for those regions. The relationship between Europa Clipper and any future Europa lander is similar to the relationship that existed between the Cassini-Huygens mission to Saturn and the proposed follow-up missions to Titan. Cassini characterized Titan in enormous detail through repeated flybys and one descent probe. Those measurements gave Dragonfly, the next major Titan mission, scheduled for launch in 2027, the targeting data and scientific justification needed to be approved as a follow-up. Europa Clipper is intended to serve the same purpose for Europa. It is a reconnaissance mission for the deeper investigations that may follow. This is also part of why the patience of the timeline matters. Europa Clipper arrives at Jupiter in 2030. The primary mission runs through 2034. Any follow-up Europa lander mission, if approved on the basis of Clipper's findings, would not arrive at Europa before the mid-2040s at the earliest. The complete cycle of investigation, from current uncertainty through Clipper's characterization to any direct life detection effort, spans something like 20 years. That is a long time. But it is the actual timeline of how serious astrobiology gets done at the outer solar system. We are looking at the part of the timeline where the questions get defined more clearly than they currently are, not the part where the final answers arrive. There are three serious ways to interpret the current state of Europa science, and they will be tested directly by Europa Clipper over the coming decade. Each interpretation has supporting evidence. Each one has weaknesses, and the choice between them is not yet settled in the technical literature, despite the more confident framings that have appeared in popular coverage. The first interpretation, which is the most conservative, holds that Europa's ocean is essentially isolated from its surface. The ice shell is thick, perhaps 20 kilometers or more, and acts as a near-permanent barrier. The chaos terrain regions are remnants of past disruption events that occurred during particular epochs in Europa's history, but are not currently active. The plume detections of the past decade, where they were not directly refuted, were sampling occasional small-scale brine pocket venting from within the ice shell, rather than direct connections to the deep ocean. The CO2 in Terra Regio is real, but it was emplaced long ago, during a period of geological activity that has since ceased. Under this interpretation, Europa's ocean may be habitable in principle, but it is chemically isolated from the surface oxidant supply that would create a redox gradient. The ocean's habitability case depends on whatever hydrothermal activity might be occurring at the seafloor, plus whatever chemistry was present at the ocean's formation. This is still scientifically interesting. Earth's deep ocean hydrothermal vent ecosystems exist without significant surface chemistry input, and Europa's ocean could, in principle, support similar chemistry through purely internal processes. But the case is weaker than it would be if surface oxidants were actively reaching the ocean. The strongest evidence for this interpretation is the JWST plume non-detection, the recent refutations of the Sparks and Gaia plume claims, and the structural difficulty of maintaining open pathways through a thick ice shell. The accumulation of these results, particularly over the past several years, has shifted some researchers toward this more conservative view. The weakness is the JWST CO2 detection itself, which strongly suggests that some kind of exchange between the surface and the interior has occurred at some point, even if it is not currently active. The chaos terrain regions appear to be the sites of this past activity, but the conservative interpretation does not have a satisfying explanation for what triggered them or whether similar episodes might occur in the future. The second interpretation, which I would describe as the moderate position, holds that Europa's surface and ocean are connected, but intermittently rather than continuously. The ice shell varies in thickness, with regions of thin ice, possibly in chaos terrain, where pathways from the ocean to the surface can open during specific tidal stress conditions. Plume activity, when it occurs, is rare, transient, and localized to these regions. The plume detections of the past decade may have caught some of these events, though most of the individual detections have not held up to scrutiny. The CO2 in Terra Regio represents an episode of past venting that has left a chemical signature on the surface. Under this interpretation, Europa's ocean has periodic access to surface oxidants, even if that access is not continuous. The habitability case is moderately strong, because a redox gradient that operates intermittently is still a redox gradient. The chemistry of the ocean would be different from what it would be under continuous exchange, but it would not be the same as a fully isolated ocean. Life, if it exists, might be adapted to these intermittent conditions in ways that we cannot easily predict from terrestrial analogs. The strongest evidence for this interpretation is the combination of the JWST CO2 detection, which requires some exchange to have occurred, and the JWST plume non-detection, which requires that exchange to not be currently active in the regions observed. Both observations are consistent with intermittent activity, rather than either continuous activity or complete isolation. The weakness is that we do not yet have direct evidence of any specific connection mechanism. The chaos terrain hypothesis is plausible but unconfirmed. We do not know how often these connection events occur, what triggers them, or whether they are occurring somewhere on Europa right now that simply has not been observed. The third interpretation, which is the most optimistic from an astrobiology perspective, holds that Europa's surface and ocean are actively connected through ongoing geological processes, even if those processes have been hard to detect from Earth. Plumes may occur regularly, but they may be smaller, more transient, or more localized than the most dramatic Hubble interpretations suggested. The chaos terrain regions may be sites of currently active surface-ocean exchange. The ice shell may be thinner than current estimates suggest in some regions. The ocean is chemically rich, energetically active, and continuously receiving oxidants from the surface. Under this interpretation, Europa's ocean is one of the most promising places in the solar system to look for life. The habitability case is strong because the redox gradient is sustained. The conditions for life as we understand it, liquid water, energy sources, chemical building blocks, are not just present but actively maintained by ongoing processes. The strongest evidence for this interpretation is the JWST CO2 detection in chaos terrain. The surface salt distribution patterns identified by Hubble and Galileo, and the broader pattern of geological youth visible across Europa's entire surface. The lack of impact craters, in particular, suggests that the surface is being actively resurfaced on relatively short geological timescales, which implies active geological processes connecting the surface to the interior. The weakness is that direct evidence of currently active surface-ocean exchange remains elusive. The most dramatic plume detections of the past decade have been weakened by subsequent analysis. JWST did not see active venting. The bold interpretation requires that the activity exists, but is happening at a level too subtle for Earth-based observation to consistently catch. Europa Clipper will discriminate between these three interpretations, not necessarily with a single dramatic finding, but through the accumulated weight of 49 flybys, multiple instrument datasets, and 4 years of sustained close-range observation. The mission was not designed for any single one of these interpretations to be correct. It was designed to determine which one is. Here is what makes this all worth paying attention to, even with all the caveats and refutations and uncertainties that the actual science requires. For the first time in human history, a spacecraft is on its way to make detailed measurements of a confirmed ocean world beyond Earth. Not a hypothetical ocean, not an inferred one. An ocean whose existence has been established by multiple independent lines of evidence over decades. An ocean that, by current estimates, contains more water than all of Earth's oceans combined. That ocean has existed, in some form, for most of Europa's history. It has been chemically interesting throughout that time. It has been subject to tidal heating, to potential hydrothermal activity, to whatever exchange with the surface has occurred. We have, at minimum, billions of years of complex chemistry running in a stable environment of liquid water. Whether or not that chemistry produced life is a question we cannot answer from Earth. We cannot answer it from any reasonable telescope observation. We may not be able to answer it definitively even with Europa Clipper. The mission is designed to characterize habitability, not to detect life directly. Life detection, if it becomes scientifically justified, would likely require a follow-up mission, a Europa lander, or an ice-penetrating probe, capable of in-situ chemical analysis at the surface or below. But Europa Clipper will tell us what we are dealing with. It will tell us how thick the ice is. It will tell us what is dissolved in the ocean, to the extent that surface chemistry preserves a record of it. It will tell us whether surface and ocean are connected. It will, if plumes exist and Clipper catches one, give us the first direct sample of material from another world's interior ocean. The mission has not arrived yet. It is in transit. The Mars flyby is complete. The Earth flyby is upcoming. The Jupiter arrival is still 4 years away. And then, 49 flybys, spread across nearly 4 years of primary mission, will accumulate the data that will define what we know about Europa for at least a generation afterward. The story is genuinely incomplete. It will remain incomplete for years. What we have now is the prelude, the body of evidence that motivated the mission, the open questions that the mission was designed to answer, and the most recent refinements and refutations of earlier claims that have shaped our current understanding. What we do not have yet is the answer. There is one more piece to this story worth flagging. Europa is not the only outer solar system body with a confirmed or strongly suspected subsurface ocean. The pattern that has emerged over the past 2 decades, across multiple missions to multiple worlds, suggests that subsurface oceans may be one of the more common features of large icy moons throughout our solar system. Saturn's moon, Enceladus, has actively venting plumes that have been directly sampled by NASA Cassini spacecraft, with confirmed water vapor, salts, organic molecules, and molecular hydrogen. A chemical profile that has driven enormous interest in Enceladus as a habitability target. The Enceladus plumes are continuous, well documented, and have been studied at higher resolution than Europa's hypothetical plumes have ever been. Cassini flew through them repeatedly between 2005 and 2017. The chemistry detected during those fly-throughs included molecular hydrogen, which on Earth is one of the key energy sources powering microbial life at deep-sea hydrothermal vents. The Enceladus case is, in many ways, a stronger astrobiology case than Europa's based on current evidence. Future missions to Enceladus are being actively planned, including concepts that would directly sample its plumes for organic molecules and even potential biosignatures. Jupiter's moon Ganymede also has a subsurface ocean, confirmed by Hubble magnetospheric observations published in 2015, with European Space Agency's JUICE mission, the Jupiter Icy Moons Explorer, currently in transit and scheduled to arrive at Jupiter in 2031 to study Ganymede in detail. Saturn's moon, Titan, has a confirmed subsurface ocean, plus a methane-based weather cycle on its surface and a chemistry rich in organic molecules. NASA Dragonfly mission, scheduled for launch in 2027 and arrival at Titan in 2034, will explore Titan's surface chemistry directly. The outer solar system has become, over the past 20 years, a region of intense astrobiological interest. The traditional concept of the habitable zone, the narrow ring around a star where liquid water can exist on a planetary surface, has been challenged by the discovery that tidal heating can maintain liquid water environments far beyond the conventional habitable zone, in subsurface oceans protected from radiation by overlying ice shells. If this discovery generalizes, if tidally heated ocean worlds are common around giant planets throughout the universe, then the total inventory of potentially habitable environments in any given star system is far larger than traditional models suggested. Europa is the first of these worlds we will study in detail. Whatever Europa Clipper finds will not just inform our understanding of Europa, it will inform our understanding of the entire class of icy ocean worlds: Ganymede, Titan, Enceladus, Triton, and the unknown number of similar bodies orbiting giant planets in other solar systems. That is the broader stakes of the mission, not just whether one specific moon has plumes, but whether one specific test case can tell us what kind of habitability is possible across an entire category of worlds. So, what does the honest current picture of Europa actually look like as of mid-2026? The ocean is real. This is established by the induced magnetic field measurement and is not seriously contested. The ocean has been liquid for most of Europa's history. It contains salt. It is in thermal contact with the rocky interior beneath. It is, in principle, capable of supporting the conditions for life as we understand life on Earth. The chemistry of the surface is real and informative. Carbon dioxide is concentrated in chaos terrain in patterns that suggest internal transport. Salts are distributed in ways consistent with ocean-derived material. Hydrogen peroxide and other oxidants are present on the surface from radiation processing. The geological record of Europa's surface preserves evidence of past dynamism even where current activity is not detectable. The plume question is genuinely unsettled. The Roth 2014 detection has not been independently reproduced. The Sparks 2016 interpretation has been substantially weakened by subsequent analysis. The GEA 2018 interpretation has been challenged by Patterson and Collinson in 2026. The JWST observations failed to detect active venting at the time they were taken. None of this proves that plumes do not occur. But the confident Europa is venting water framing of much popular coverage is not supported by the current weight of evidence. The habitability case for Europa does not depend on plumes. It depends on the ocean, the chemistry, and the potential for surface-ocean exchange, all of which Europa Clipper will assess directly through measurements that do not require plumes to exist. There is one further consideration worth mentioning, which is the question of how the popular framing of Europa as an alien life candidate has shaped both the funding case for the mission and the public expectations for what it will find. Europa Clipper was approved and funded over many years, through several different presidential administrations and many different congressional appropriations cycles. The case for the mission, in its public-facing framing, has consistently emphasized the search for life. The plume detections of the past decade played a meaningful role in maintaining political momentum for the mission, by providing concrete-sounding evidence that Europa might be doing something we could directly observe. If the plume evidence weakens further, or if Europa Clipper arrives and finds no evidence of active venting at any of its 49 flybys, the public framing of the mission will have to adjust. The scientific case for the mission will not collapse. The ocean is still there. The chemistry is still informative. The structural questions about the ice shell are still worth answering, but the headline narrative that has driven public interest may need to be replaced with something more measured. This is a legitimate concern that researchers in the field have privately discussed for years. The tension between honest scientific communication and the political and funding realities of large flagship missions is a real one. Europa Clipper exists in part because the public has been told a particular story about Europa for 2 decades. Adjusting that story in real time as the evidence evolves, is part of the responsibility of researchers and journalists who care about the long-term credibility of planetary science. This video has tried to do that adjustment honestly. The mission is still worth doing, the questions are still real, the ocean is still there. But the specific claims that Europa is actively venting water into space, that those plumes have been confirmed by multiple instruments, that we already know enough to be confident about what Europa is doing. Those claims are not supported by the current evidence, and pretending otherwise will not help anyone when the mission arrives and the actual measurements start coming in. The mission is on its way. It launched on October 14th of 2024. Its Mars flyby is complete. Its Earth flyby is upcoming. Its Jupiter arrival is in April of 2030. The 49 close flybys of Europa will define our understanding of this moon for a generation. That is where the story actually sits, in plain language, with the caveats and uncertainties intact. Tonight, we did not just learn about a moon that may or may not be venting water. We watched what happens when a planetary science question gets caught between the careful pace of actual scientific investigation and the much faster pace of popular coverage. We saw the original detections, Roth in 2014, Sparks in 2016, Gaia in 2018. Each one announced with appropriate scientific caution and then translated by press coverage into more confident framings than the underlying papers supported. We watched the slower process of follow-up analysis, Roth's own unsuccessful attempts to reproduce his detection, Jeannot's 2020 refutation of the Sparks interpretation, Patterson and Collinson's 2026 refutation of the Gaia interpretation, receive far less coverage than the original claims, even though those refinements are central to the current scientific picture. We watched JWST, in 2023, deliver findings that emphasized the carbon dioxide detection while leaving the plume non-detection in the background of popular coverage, even though both results are equally important for understanding what Europa is actually doing right now. And we watched, in the broader pattern, how the popular story about Europa came to differ from the technical story. Not because anyone was being dishonest, but because the structure of science journalism rewards dramatic confirmations more than careful refinements, and because the original detections, even when they have been substantially weakened, continue to be cited as if the early framings still held. This is not a story about a moon. It is, in part, a story about how we transmit scientific information through a media environment that tends to compress nuance and hedge less than the original researchers did. It is a useful case study, regardless of what Europa Clipper finds when it arrives. And yet, even now, the genuinely interesting questions remain genuinely open. We do not know how thick Europa's ice shell is in detail. We do not know whether the chaos terrain regions are sites of current activity or only ancient activity. We do not know whether plume activity, in any form, is occurring at present. We do not know whether the ocean has the chemical architecture to support a sustained redox gradient. We do not know whether 4.5 billion years of stable liquid water environment is enough, by itself, to produce the kind of molecular chemistry that, on Earth, eventually produced life. We do know that Europa is the most promising place in the outer solar system to investigate these questions. We do know that one of the largest planetary science spacecraft ever built is on its way there now. We do know that, by 2034, we will have answers to most of the structural questions about Europa's interior, surface, and ocean that we currently can only speculate about. The mission is patient. It is careful. It is not designed to produce a single dramatic announcement, but to accumulate a comprehensive characterization of a single icy moon over many years. That patience is, in some ways, the most appropriate response to the actual state of Europa science. We have made dramatic claims for a decade, and most of those claims have not held up under scrutiny. The next generation of evidence will come from 49 carefully planned flybys, from instruments that have been calibrated for exactly this purpose, from a mission that was designed precisely to do what individual telescope observations cannot. There are a few things worth taking from this story that go beyond Europa itself. The first is the difference between confirmation and absence of refutation. Several of the Europa plume detections were treated, in popular coverage, as confirmed for years after their initial announcement. In several cases, the actual scientific status was always that the detections were candidate evidence that had not yet been refuted. When refutations finally came, they did not change the actual scientific status as dramatically as the press coverage shifts would suggest. Most of the careful researchers had already been treating the detections as tentative. The popular coverage had jumped ahead. The lesson here is methodological. The status of a scientific claim depends on the underlying evidence and how that evidence has held up to scrutiny, not on how confidently the claim has been reported. A claim that has been in the news for 10 years is not necessarily a claim that has accumulated 10 years of supporting evidence. It may instead be a claim that was announced once with appropriate hedging and then cited repeatedly without revisiting the original caveats. The second is the asymmetry of scientific news. Dramatic, positive claims receive more coverage than careful refinements. This produces a public picture of any active scientific question that is consistently more confident than the underlying evidence supports. This is not a problem unique to Europa. It applies to most active areas of scientific research. Being aware of it is a useful intellectual hygiene. Whenever you read a confident framing of an active scientific question, particularly a question at the frontier of any field, it is worth asking whether the most recent technical literature actually supports that level of confidence, or whether the confidence is a residue of earlier dramatic claims that have since been refined or weakened. The third is the difference between a mission's scientific case and any individual claim within that case. Europa Clipper was funded and built on the basis of the ocean, established by the induced magnetic field measurement, which has never been challenged. The plume question was secondary motivation, useful but not necessary. When the plume evidence has weakened, the mission's core scientific case has not weakened. The ocean is real. The ice is interesting. The chemistry is potentially habitable. Whether plumes also exist is a question the mission can answer, but the mission would still be worth doing if the answer turns out to be no. This is an important distinction. Flagship missions like Europa Clipper take decades to design, build, and launch. The scientific landscape evolves during those decades. The case for the mission has to be robust enough to survive evolution in the secondary motivations, as long as the primary scientific case remains intact. For Europa Clipper, the primary case, the ocean, has remained intact for the entire development period. The fourth is the value of in situ measurement over remote observation. The reason the Europa plume question has been so contested is that all of the relevant observations have been made from Earth or near-Earth space, where the sensitivity limits are severe and the signals are often marginal. Europa Clipper, by going to Europa and flying within tens of kilometers of the surface, will produce measurements at a sensitivity that no telescope can match. Many of the questions that have been argued for a decade will be settled by direct measurement within the first year of the mission's primary phase. This is one of the more important reasons that planetary science is worth investing in, even in an era of extraordinary advances in Earth-based and near-Earth telescopes. There are some questions that simply cannot be answered remotely. Direct measurement at the target body, with instruments designed specifically for that purpose, remains the gold standard for any contested question about a specific world. And the fifth is this: the honest, current picture of Europa is more uncertain than the popular version of it has suggested for several years. That uncertainty is not a failure of science. It is what science genuinely looks like when an active research question is being argued at the frontier. The certainty will come from new data, not from confidence in old interpretations. The popular version of any scientific story tends to compress nuance and to project more certainty than the underlying literature supports. Real science is messier. Real science involves dramatic claims that get refined, refuted, defended, refuted again, and eventually either confirmed by better data or abandoned in favor of newer interpretations. Europa is currently in the middle of one of those messy phases. Europa Clipper will help clean it up, so I want to leave you with a few questions tonight. What does it mean to send a spacecraft to a place we have never been, knowing that some of the central reasons we are sending it may turn out to have been overstated by the time we arrive? Is the mission justified anyway? On what grounds? How do we, as people who are interested in space science but who do not work in it ourselves, calibrate our confidence in claims about distant worlds? When does a popular framing represent the actual state of scientific knowledge? And when does it represent something that has shifted in the underlying literature without the coverage catching up? And what does it mean that, even with the plume question weakened, Europa remains one of the most scientifically promising places in the solar system to investigate the question of whether life exists beyond Earth? Sit with those for a moment. They are bigger than Europa. If this story stayed with you, tell me in the comments which part landed hardest. Was it the Patterson and Collinson 2026 paper that refuted one of the strongest pieces of Europa plume evidence just months before this video was made? The pattern of dramatic detection, followed by quiet refutation, that has played out across multiple lines of investigation. The JWST observations that emphasized carbon dioxide, while the failure to detect plumes received far less attention. Or the realization that Europa Clipper, when it finally arrives, will give us the first real direct measurements of an ocean world beyond Earth. Measurements that will resolve a decade of contested interpretations through sheer proximity to the moon itself. I want to know. And if you want more stories like this, real science, full context, mystery preserved where it actually exists and dispelled where it does not, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. The mission is in transit. Europa is waiting, where it has been for 4.5 billion years, with an ocean beneath its ice that no instrument has ever directly sampled. In April of 2030, that begins to change. Until then, the most honest thing we can say about Europa is also the most useful thing. We do not yet know, but we built a spacecraft to find out, and it is on its way.